Hello friends, myself Dr. Nandakumar Raubavale is going to deal with Applied Thermodynamics 1. This is our 20th lecture. So in previous lecture we have discussed temperature entropy diagram, enthalpy entropy diagram, reheat cycle, regenerative cycle. Today we'll discuss about the efficiency of indirect contact heating and the numerical on vapor power cycle. So in previous class, one more thing we discussed about direct contact heating cycle. What this direct contact heating cycle was. So there were heaters. There were heaters provided. The heaters which were provided were direct contact. So here the condensate and the steam were going to mix with each other. But in this case, the feed heater 1 or feed heater 1 and 2, here we have feed heater 1 and heater 2, say we call this as 1 and this we call as 2. So these two heaters are not the direct contact mixing type. Means the condensate coming out of this condenser is not going to mix with this steam, so it passes through one tube and this surrounds the tube. So that is why we can say that it is a non-mixing or indirect contact heating. So how it works, that we will see. Let us consider point B, which is outside the boiler. So from this boiler a superheated steam comes out at point B, which has got pressure PB, boiler pressure PB, and temperature of steam as a superheated. Ts is the temperature of superheated steam, pressure of steam is boiler pressure PB, and when it comes out we call that as a steam as a superheated, and that superheated steam of 1 kg, we consider 1 kg of steam, mass of steam is 1 kg of steam enters into the turbine at point B, say. When it enters into the turbine at point B, that point B is represented on TS diagram. Here this point B is represented here on TS diagram. So condition of steam is pressure is PB, temperature is TS, and 1 kg of steam comes up. Then it enters into the turbine here. When it enters into the turbine, 1 kg of steam is expanded from point B to 1. So it is expanded from point B to 1, so that pressure falls it up to P1. So at point 1, when pressure becomes P1, here the steam is expanded isentropically, we can see here. Steam is expanded, 1 kg of steam is expanded from point B to 1 isentropically, and when pressure reaches to P1, at pressure P1, so this expansion is discontinued. Say for example m1 kg is taken out and rest of the steam is allowed to expand further. So the steam of m1 kg is blended out or is taken out, and rest of the steam, that is 1 minus m kg, 1 minus m1 kg is expanded. So m1 kg is taken out of 1 kg, m1 kg is taken out, means rest of the steam is 1 minus m1 kg is expanded till the pressure falls up to P2. So when pressure becomes P2, again m2 kg is taken out or blended out, and rest of the steam means 1 minus m1 minus m2 kg of steam is again expanded from point 2 to C. So here we can see at point B it enters, 1 kg is expanded from B to 1, and from at point 1 the m1 kg is taken out and 1 minus m1 kg is again further expanded, then m2 kg is taken out, again 1 minus m1 minus m2 kg is expanded, and 1 minus m1 minus m2 kg of steam and comes out is supplied to condenser at point C. So at point C, steam coming out turbine enters into the condenser. We can see here steam coming out of this turbine at point C, that is condenser pressure PC, is entering into the condenser. So here first m1 kg, first initially 1 kg is expanded, then 1 kg which enters, this 1 kg is expanded, m1 kg is taken out, then m2 kg is taken out, rest of the steam is 1 minus m1 minus m2 kg is condensed. Up to point 3 it is condensed. So steam after getting condensed comes out of this condenser, and with the help of pump, say for example pump P1, so here pump P1 pressurizes this steam from pump work PW1, we can call as pump work 1 is applied here, and this steam pressure is increased from condenser pressure to the direct boiler pressure. So here we can see here this pressure P2 does not allow, is not allowed to mix with the steam condensate. So therefore this pressure which is to be increased by this pump is not up to P1 or P2. The pump is used to increase pressure of this condensate from condenser pressure directly to the boiler pressure, because it is supplied directly into the boiler. So there is nothing which is going to mix in this condensate. Therefore this condensate coming out of this condenser is supplied directly into the what you call a boiler. So pressure is increased from PC to P4 at 4, 5, 8, 6, and say this is point 11. So at up to point 11 pressure is same. So this is constant pressure line PB, and this is constant pressure line P1. Then this is constant pressure line P2. So here pressure is increased from condenser pressure directly to the boiler pressure. So steam is condensate is directly supplied into the boiler. So first this condensate enters into the first heater 1. So when this pump increases its pressure from 3 to 4, means condenser pressure PC to the boiler pressure PB. So this is a boiler pressure line. We can call this line as a boiler pressure line PB. So on this line the pressure is going to be constant. Now the condensate is supplied from point 3 to 4, that is it is injected into the boiler. So when it is injected into the boiler, so here the heat exchange takes place. So here m2 kg of steam which is taken out blended is going to give its heat to the condensate which is of having mass 1 minus m1 minus m2 kg. So there is exchange of heat. So here what happens, m1 minus m2 m1 minus m1 minus m2 kg of steam condensate increases its enthalpy from 0.4 to 0.5, from 4 to 5, you can see here. So enthalpy of condensate is increased from 4 to 5. After 0.4 it enters into the heat exchanger we call as a feed heater, and enthalpy changes from 0.4 to 5. So it helps us to increase enthalpy of this condensate from 4 to 5. Whereas how this enthalpy is increased, it is at the expense of enthalpy of this steam m2 kg. So m2 kg of steam which enters into this heater at 0.2 and comes at 0.7 out at 0.7. So there is decrease in the enthalpy of m2 kg of steam. So m2 kg of steam loses its enthalpy from H2 to HF7. So this decrease in the enthalpy helps us to increase in the enthalpy of condensate. So decrease in the enthalpy of steam is transferring heat to the condensate to increase its enthalpy from 4 to 5. So after that, this condensate enters into the second feed heater. When it enters into the second feed heater, we can see here in second feed heater again m1 kg of steam enters. M1 kg of steam gives its heat to the 1 minus m1 minus m2 kg of condensate, and again it increases its enthalpy. So from 0.5 to 6 again the enthalpy increases. So you can see here from 0.5 to 6 enthalpy of steam is increased, condensate is increased, and that is obtained by transfer of heat of m1 kg of steam. M1 kg of steam gives its heat to the 1 minus m1 minus m2 kg of condensate, So here 1 minus m1 minus m2 kg of condensate absorbs heat energy from m1 kg of steam and it increases its enthalpy from 0.5 to 6. So F6 minus HF5 is the increase in enthalpy of condensate, whereas the enthalpy of steam decreases from H1 to HF9. So after that, this water or condensate which comes out of this condenser at comes out of feed heater 2 directly is supplied into the what you say boiler. So before it is supplied to the boiler, everything goes into the boiler here. Now we can see here this m2 kg is condensed. Again m2 kg gives its heat to the condensate and therefore this m2 kg of steam gets condensed and it comes out at 0.7. So when it comes out at 0.7, the pump 2 is pumping it into the boiler. Pump 2 pumps this water into the boiler or condensate into the boiler. So pump 2 increases pressure from 0.7 to 0.8, that is from pressure P2. So here the steam which is coming out is at pressure P2. So this steam pressure is at 0.7 is P2 and this pressure is increased by pump 2 to the boiler pressure PB because this condensate has to be supplied into the directly into the boiler. It connects directly to the boiler line. Therefore, the pressure increased by pump 2 is from P2 to PB. So pump 2 is increasing pressure from P2 to PB. So here 0.7 to 8 gives us pump work 2. Pump work 2 is here from 0.7 to 8. So pump is going to supply this condensate from feed heater 1 to the boiler. Similarly, when steam comes out of this turbine, m1 kg of steam comes out of this turbine which is at pressure P1. After giving its heat into the feed heater 2, m1 kg of steam m1 kg of steam gets condensed and this condensate m1 kg of condensate is supplied by this pump number 3 into the boiler. So here pump number 3 work is shown between 9 to we can say 0.8 9 to 10 9 to 10 we can call directly it is supplied to the boiler. So here we can see from 0.9 to 10 is the increase in the pressure made by pump number 3. So pump work 3 can be obtained. After that everything enters into this boiler and from point 10 onwards, from point 10 to 11 the sensible heating takes place. So very small amount of sensible heat is added and thereafter the latent heat of vaporization is added, then enthalpy of superheat is added and then steam is expanded again in the same way. So here the work done is divided into 3 stages. So here work done 1, turbine work done 1, turbine work 2, W2 and here W3. So 3 works are done. So in first case work done 1 is done by 1 kg of steam, work done 2 is done by m1 minus m2 kg 1 minus m1 kg of steam and work done 3 is nothing but done by 1 minus m1 minus m2 kg of steam. So here the work is done by different mass of steam, not by single mass of steam. Now this is about the working of indirect contact heating cycle. Now coming to the equations related to this indirect contact heating cycle, just we will have the equations. Now work done by the steam, we have to find out where work is done and how to find out the net work done. So first of all work done by the turbine, we have to find out work done by the turbine. By turbine, work done by turbine per kg of steam. That is given by W1 plus W2 plus W. So what is W1? Work done 1. So this is the W1, work done 1. So steam is expanded from point B to 1. Enthalpy at B, enthalpy at 1 can be known. So this work done is given by HB minus H1 into amount of steam that is expanded is 1 kg plus work done 2 is done between point 1 to 2. So this is work done 2 by the turbine. So this enthalpy is going to decrease from H1 to H2. So here we can write H1 minus H2 into amount of steam expanded is 1 minus M1 kg. M1 kg is taken, so rest of the steam is 1 minus M1, because initially we are assuming that 1 kg of steam is expanded, and this is nothing but work done 3. Work done 3 is obtained by reducing enthalpy of steam from H2 to Hc. So here plus H2 minus Hc into 1 minus M1 minus M2 kg of steam is expanded. So this is how we obtain the work done. Total work done by the turbine. We can call this as a turbine work done. Then the pumps are going to consume work. So here we have three pumps, P1, P2, P3. So pump work or pump work, total pump work is given by pump work is equal to WP1 plus WP2 plus WP3. So looking at this, WP1, pump 1 is working here, pump work WP1 is from point 4 to 3 to 4, then 7 to 8 is pump work 2, and pump work 3 is from 9 to 10. So pump work 1 can be obtained here. Pump work 1, this first pump is going to supply 1 minus M1 minus M2 kg of condensate. So here mass of the condensate is 1 minus M1 minus M2 into specific volume of condensate into pressure increased is from PC, pressure is increased from PC to the boiler pressure PB. So PB minus PC is taken here. Then after that, this pump work 2, second pump is going to supply this M2 kg of condensate. Only M2 kg of condensate is supplied from pressure P2 to boiler pressure directly. So here M2 into specific volume of liquid into pressure increased from boiler pressure to P2, PB minus P2. And third pump work, that is nothing but mass M1. So M1 is the mass of steam, sorry, condensate, which is supplied from point 6 to, sorry, 9 to 10. So here M1 into VW into pressure is increased up to boiler pressure, initial pressure is P1. So at this condensate is as pressure P1, therefore PB minus P1. So net work done can be obtained by Wn. We can call this as equation number 1. Above equation is 1. We call this as equation number 2, say. So net work is equal to turbine work, total turbine work minus total pump work. We can call this as WT minus of WP. So net work is nothing but the work produced minus work consumed. So pumps are work consuming devices, turbine is work producing device. So net amount of work that is going to remain is turbine work minus pump work. So now we will find the heat supplied per kg of steam. So heat supplied per kg of steam is equal to, that is given by where heat is supplied actually. So heat supply starts at 0.4, but actually from 0.4 to 5 heat is not supplied in the boiler, it is outside the boiler. So this steam M2 kg is giving heat to increase its enthalpy from 4 to 5. Then from 5 to 6 heat is supplied by M1 kg of steam, and from 0.6 onwards this uh, enthalpy is increasing. After 0.6 the enthalpy is increased in the boiler. So this liquid M1 kg of condensate enters at 0.10, this condensate enters at 0.8, this condensate enters at 0.4. So there is no fixed location at which this condensate is entering. Therefore, the final state of steam is known. So finally, amount of enthalpy at point B we can find out at point B. So that will be HB. Final enthalpy is HB minus of HFX. HFX is nothing but, say here it is varying from 0.4 to 0.6. So enthalpy at which point we have to consider it is not that much clear, but here we can say that this enthalpy is increased from 4 to 5 by this steam. This enthalpy is increased by a steam of M1 kg, and from 0.6 and 10. So there is exactly the difference. It is not going to increase from 0.6 or 0.10. So in between, sensible heat is added from point in between 6 to 10 up to say 0.11. So this much amount of sensible heat is added, then latent heat of vaporization, then superheat. So this point is taken as HF. So HFAX. So this is equation number say 3. So heat supplied is calculated in this way. Therefore, uh, this HFX is enthalpy of feed water entering the boiler. What this HFX is the average enthalpy where HFX is the average enthalpy of steam entering the boiler. This average enthalpy. Now, to find out efficiency, we know this net work done and heat supplied. Therefore, the efficiency of indirect contact heating cycle is given by efficiency of regenerative cycle. We can call net work done Wn divided by heat supplied. This is nothing but turbine work minus pump work divided by Hb minus Fx into 100. That will be in percentage. Now considering heat balance for feed heater 1 and feed heater 2. So heat balance, considering heat balance for heater number 1 and heater number 2. And 2. What we can do is, in first heater we say here, this is first heater, M2 kg of steam is going to give its heat. So heat given by M2 kg of steam is H2 minus HF7, and M2 is the mass of steam. So we can write here heat given by the steam is M2 into H2 minus HF7, and this amount of heat is utilized by this 1 minus M1 minus M2 kg of condensate to increase its enthalpy from 4 to 5. So here we write as 1 minus M1 minus M2 kg of condensate utilizes its heat to increase enthalpy from 0.4 to 5. We write this as HF5 minus HF4. So again we can say that this M2 as it is, H2 as it is, we write HF7 is, we will write as it is equal to 1 minus M1 minus M2 into, in place of HF5, HF5 is very close to 7, so we write this as HF7, and minus of H4 is, if we neglect pump work is very small. If we neglect this pump work, so enthalpy at point 4 is equal to enthalpy at point 3. So there we can write as HF3. What is the assumption? HF5 is equal to HF7 and HF4 is equal to HF. So this is the assumption to write heat balance for first heater. Then looking at the second heater, to write the equation for second heater, if we see for second heater, we can write here in the second heater M1 kg of steam is giving heat to reduce its enthalpy from 1 to 9. So here we can write M1 kg of steam is giving its enthalpy to reduce its enthalpy from H1 to HF9, and this enthalpy is given by this M1 kg of steam to this 1 minus M1 minus M2 kg of condensate to increase its enthalpy from 0.5 to 6. So therefore we can write mass of condensate is 1 minus M1 minus M2 kg into, it increases enthalpy from 0.5 to 6. So here HF6 minus HF5 we can write, and further we can write it as M1 into H1 minus HF9 is equal to 1 minus M1 minus M2 into HF6. 0.6 and 9 are very close, so enthalpy at 0.6 is equal to enthalpy at 0.9. So HF9 we write minus, so HF5 is equal to HF7 already we have assumed. So here HF7, what is assumption is HF6 is equal to HF9 and HF5 is equal to HF7. So here pump work is neglected. I am neglecting this pump work. Assuming that 1 minute, F9, F7. So this is how for this heat exchanger 2 we have this equation. So this is, say, equation number 3, this is equation number 4, and this is number 5 for heat balance. Now coming to next equation, HF7 and HF9 are saturation enthalpies. HF7, why we are going to assume that HF5 is equal to HF9, these are saturation enthalpy. So if 0.7 is on this curve, we call this as a saturated liquid.